Thank you for Silvio, who's here live, and everybody who'll be watching this online. Just pray that you'd help me to make these things clear and intelligible, to truly teach, help them to truly learn. As we prepare for the end of this year, help us not to grow weary. We've got a test coming up soon, and then another just almost back to back. So we're just enlightening our minds. We pray this in Jesus' name. Amen. All right, my friend. So we've come into a point of going back and forth between molality and molarity, and then we even had the mole-mole fraction. I think that's a little easier to do, but the molality and molarity can be a little tricky, especially in reverse. So I want to look at this, and maybe one more time. Excuse me. So we were on the follow-up to example 11.5. I think it's going to be worth maybe doing 11.5 one more time. And we'll do it real quick. Ignore what you've already got. Let's work through it like it's fresh. And then we'll do a kind of a made-up one after that. So what we're given here is an aqueous solution of 0.556 molar, right? And so we know what that means. It's 0.556 moles of solute over 1 liter of solution, right? That matters. Okay, and we're given a density. Density equals 1.04 grams per milliliter. And we're told that it's C6H12O6. So we need the molar mass of that. Right, and so the molar mass of that is, I didn't write it down the other day, yellow. I don't even see it right on here. 180.2 grams per mole. So what we're going to do is we're going to get from moles, or from molarity to molality. Molarity is, of course, moles of solute over liters of solution. And that includes both the solute and the solvent. And we want to get to molality, we want only moles of solute over the mass of salt, 1 kilogram, right? Yeah. Okay. All right. So we absolutely have to know our density. We also are going to have to account for the mass that our solute has, right? So as we break this problem down, we've got, as we said, 0.556 moles of solute over 1 liter of solvent. All right, so we want to compute the mass of 1 liter. Oh, I did this wrong. This is of solution. Solution. We want to know the mass of this, right? Of 1 liter of this. To do that, we got to know the density, right? Mm-hmm. So this is over 1 liter. 1 liter times 1.04 grams per milliliter. I can just right here convert this to kilograms per liters, right? I don't need to go crazy with anything. And that's going to help me later, because I'll already be in the right units for what I want. So when I do this, this gives me 0.556 moles of solute over 1.04 kilograms of solution, right? Now, I'm going to need to take out the mass of my solute from my solution to figure out the mass of my solvent, right? So, I need 0.556 moles of C6H12O6 times the molar mass, which is, I'm going to go ahead and put this into kilograms right now, 0.1802 kilograms per mole, right? And when I run that math, what do you get?
Get 0.1002.
0.1002 kilograms. Oh, do that again. 0.1002 kilograms. Okay. So, this mass is for both my solute and my solvent. If I subtract my solute from my solvent, or from my solution, I'll be left with my solvent. So I know I've got 0.556 moles of solute. When I take my 1.04 kilograms and I subtract 0.1002 kilograms from it, I get?
I just did the bottom one. The bottom one is 0.9398.
0.9398, right?
Yeah.
So now, this is moles of solute. This is kilograms of solvent. Everything here is in the form that I want. I have all the right units in all the right places. I just got to do the math, and I'll be left with my molality, right? So you divide that. Do you have it for me?
0.6.
Equals 0.6. Close enough. 0.6 moles. That's what we want. We got to be able to do that. Now I'm taking the time to bring this back. This is important. This is something that, and I say it's important, well, it makes it important. These are the kind of conversions that you do in solution chemistry quite a bit. This is just so practical in lab situations and in other future chem classes that you may take. So, we want to spend a little extra time here making sure that this is solid. I'm also basically just letting you know this will be heavy on the test. Not this next test, because this will be on the one after that, right? The next test is simply chapter 10, I believe.
Yeah.
Is it right?
It's right there.
Yeah, just chapter 10, okay? So this will be on exam number 4, but the ability to go in and out of molality, molarity, and mole fractions will be heavily emphasized on that test. So bear that in mind. All right. Well, let's move on. We need to now be able to go in reverse. So we're now going to go from molality to molarity. Little m to big M. Okay? So they only give you one practice, and it's only the follow-up to the other. We're going to do the one they give us, and then I'm going to add one to it, because I think we need it. Okay. So they say nitric acid, that's HNO3 aqueous, is commonly available as a 33.7 molal aqueous solution. Tells us that our density is 1.35 grams per milliliter. It wants to know the molarity of this solution. Well, we need one more thing here. Let's take the time to figure out the molar mass of nitric acid here. Right, so 3 times 16 plus 15. So what's that? 32, 48, 58, 64. Does that sound right?
Yeah. So 3 times 15.
Confirm that. 16 times 3 plus 14 plus 1 equals 63. How did I get that wrong? Okay. 63, not 64. Okay, 63 grams per mole. Okay. So we have a 33 molal solution, right? We have its density. So that tells me right away that I have 33.7 moles per 1 kilogram of solution, of solvent. Right? Okay. All right. First thing that I'm going to recommend in solving this problem is to get everything into kilograms or grams, whichever one, and that's going to be really useful. So we're going to use our molar mass right away, right? Times 63 grams per mole. Moles will cancel, and so when I multiply 33.7 times 63, it's going to give me 2,123.1 grams of solute per 1 kilogram of solvent. Okay. Now, when I deal with molarity, molality was moles per kilogram of solvent, but when I do with molarity, I want moles per liter of solution, which means I need both my solvent and my solute. Well, I know at least my mass of my solvent and my solute, and then I know a density of the two, right? Add them and then multiply them, and that will help me, right? So I'm going to think of it this way. I've still got my 2,123.1 gram. Actually, I'm not going to need that again after this. I'm going to ignore that for a second. I've already done the math. I know that that is 33.7 moles, right? We know what that is. I went to this because when I add these together, that's going to give me my mass of my solution. So I know my mass of my solution is, this is equal to 2.123, or I can go another way. I can multiply this and go, hey, that's 1,000 kilograms of solvent, right? I'm going to do, or 1,000 grams of solvent. I'm going to go that way so that I can get in the right units, because I need grams when I do my density. So this is going to give me 3,123.1 grams of solution, right? Well, now I've got moles per solution mass. I'm getting close. The next thing that I need to do is convert from mass to volume, and I can do that given my density, right? So this is going to give me 33.7 moles of solute over 3,123.1 grams times, now I want to have 1 milliliter. I should have gone the other one.
No, that's okay.
Yeah, we'll be all right. 1 milliliter over 101.35 grams of, would have just been convenient if I'd have left it in kilograms, because then I could have just done all that. But anyway, I added a step, thinking I was saving one. And then once I do that, I'm going to multiply by, I can actually do it right now though, can't I? I can multiply by 1,000 milliliters per 1 liter. My grams will cancel, my milliliters will cancel. I'll be left with moles per liter, and I'll be good. So we run that math. 33.7 moles over 3,123.1 divided by 1.35 divided by 1,000, 2.313 liters.
Yeah.
Right? And so when I do the next step, I should get something like 14.57, 14.6 molarity, moles per liter. Got it. Okay.
Yep.
Let's do another one. Okay. So I've got, let me erase that down part two. .0 molal NaCl, where my density is 1.10 grams per milliliter, and my molar mass is 58.44 grams per mole. Okay. So I want to think of this how? What do I go first?
It's 1 mole of the solute over 1 kilo of the solvent.
Okay, good. All right, so the first thing I want to do is get this into mass, right? We'll keep it as over 1 kilogram of water. So 1 mole of sodium chloride is going to be 1.10. I mean, it's just nice when it's that simple, right?
Yeah.
I'm
58.
smart, I'll keep it like that on the test.
58.
Thank you, 58.44 grams, right?
That's good. Yeah.
Okay. All right. Now, I know this is my 1 mole, right? I don't need to do too much of that. I also know that this is going to be 1.0584 grams of solution, or kilograms, sorry. Kilograms of solution, correct?
Yeah.
Okay. Now,
Now we can multiply by the density.
okay, so that's going to give me it's going to give me 1 liter over 1.10 kilograms. These are both 10 to the negative third, so if I just multiply them both by 10 to the third, it comes out in the right ratio, right? All right, so when I do that, I get 1 mole over
0.96 22
0. What?
96
96
22
32
22
2 liters.
yeah.
All right, and find the inverse of that. I get 1.04 molar. Okay. So this is the ability to do this is going to be important. Expect at least 3 problems on this, on that test. So, all right. Well, we'll move on to the next thing then. What time you got, by the way?
130.
1:30. I know we started late, but I got to finish on time. I have a QuickBooks phone call coming at 2. All right. All right. Let's talk about vapor pressure. As described in the chapter on liquids and solids, the equilibrium vapor pressure of a liquid is the pressure exerted by its gaseous phase when vaporization and condensation are occurring at equal rates. So another way of thinking of that is graphically. So when these are coming and going at equal rates, vapor pressure is the pressure being exerted downward towards the liquid from the partial pressure of that vapor in the air above it. This phenomenon can be dissolving a non-volatile substance in a volatile liquid results in lowering the liquid's vapor pressure. This phenomenon can be rationalized by considering the effect of added solute molecules on the liquid's vaporization and condensation processes. We looked at that the other day, how they just cluster around the particles, individual particles of solvent will cluster around a particle of solute, and due to intermolecular forces, and therefore there aren't as many free to go ahead and vaporize. To vaporize, solvent molecules must be present at the surface of the solution. The presence of solute decreases the surface area available to solvent molecules and thereby reduces the rate of solvent vaporization. Thank you so much.
Thank you.
You have a wonderful, well, I'll see you tomorrow. You have a wonderful rest of today.
You too, thank you.
You're welcome. Presence of solute decreases the surface area available to solvent molecules and thereby reduces the rate of solvent vaporization. Since the rate of condensation is unaffected by the presence of solute, the net result is that vaporization condensation equilibrium is achieved but with fewer solvent molecules in the vapor phase. So here's what that's saying. If I add some solute here, right, I suddenly reduce this by a lot, right? We're now out of equilibrium, but there's nothing preventing it from driving this way to establish a new equilibrium, right? And so at that new equilibrium, I will have less at the surface and certainly less in the gas above it. Since the rate of condensation is unaffected by the presence of solute, the net result is that the vaporization-condensation equilibrium is achieved with fewer solvent molecules in the vapor phase. While this interpretation is useful, it does not account for several important aspects of the colligative nature of vapor pressure lowering. A more rigorous explanation involves the property of entropy, my favorite word. We were talking earlier about all this with evolution and everything else. Let's take a minute to talk about this word. Let me make a note, and I'll come back to it. So entropy. Entropy is the tendency of everything to go from order to disorder. The way that this plays itself out practically is everything goes from a high to low concentration. We see it with concentration. We see it with organization. We see it with, what's the word I'm looking for? Energetics. Everything does this, right? Everything in the entire universe does this. Inverse square law of light, right? So you have a source of light, the way the light spreads out. Well, how from high to low? That's following energetics. If I have a steaming hot cup of coffee and I stick it out on the desk, the coffee does not get hotter. The energy that's in the coffee diffuses, it follows entropy. It goes from high to low until it's equally distributed in the gas molecules throughout the room. This happens everywhere. This is the primary thing that drives everything we know about the universe and everything that we see. only thing that doesn't follow this is life. We are the only things that take low concentrations and turn them into high concentrations. In fact, if we can't do that, we're not alive. To be alive, you have to maintain an equilibrium, a level of stasis where things don't change. But you ate lunch and you have energy and you're producing heat because you have to, but that heat's dissipating, right? It's going from high in you to low out there. And if you can't fight that, you die, right?
Yeah.
One of the things I always say to my bio students is you're an anti-entropy machine. Like you're so good at this. The thing that gets you disease is entropy. Because you do this, you go from low to high. Low to high, you go from disorder to, you go from chaos, or from chaos to order. You go from low concentration to high concentration. And you do this amazingly well. What kills you is when you can't do this.
So we actually do the opposite of...
You do the opposite of entropy. All day, every day. And if you ever stop, you die. Think of a freshwater fish. Okay, so you throw a freshwater fish. Oh, here's a fish. It's a terrible fish, but it's a fish all the same. Okay, here's a fish. Here, make it look a little more like a fish. That's terrible. Here, it's fine. So here, we'll go fishing for him now. A little context. Here's a worm. You take a freshwater fish and you throw it in the ocean. Well, in the freshwater, there's very few solutes. The molarity or the molality in freshwater is very, very low for our salt concentration. But you put the same thing out here in the ocean. Well, now that fish is surrounded by solutes, right? And he can't avoid it. He breathes through his gills, right? So his gills are constantly coming in contact with this water. Everything flows from high to low. Solutes are high in the ocean, relatively low in the fish for salt. So it's going to flow in, changing his concentrations to a level that he cannot sustain, that will kill him. He must be able to expel that salt, or he will not survive. Well, this freshwater fish is not adapted for that. God did not give him that equipment. A saltwater fish can. If he can't live. But hypothetically, according to evolution, all life begins in something like this. But you can't live like this. Nothing can live like this, except for things that do live like this, but you have to have the machinery to pump this out. How do you go from nothing to something? This defies all the laws of thermodynamics, defies everything about entropy, and as every living thing does. This is just one example, right? Everything that's alive is perfectly adapted to the environment that God has put that each individual thing into. And that's why they can't survive in other situations, because there's so many different situations and circumstances, but each one is so uniquely, perfectly fitted for its own anti-entropy tasks. And according to physics, life is not possible. But here we are killing it, right? I don't know, so there's just one more piece of why do I believe the Bible? I believe the evidence, I see the things I see in science, but I don't, the science of thermodynamics does not agree with the science of what's called evolution. It's not possible. Well, what do you do when something's not possible? You got to go, well, I got to reevaluate this. I go, something doesn't make sense. The thing with evolution is they don't do that. They just go, we're going to pretend that's not there. You see in the fossil records, all of a sudden, things just appear. suddenly. That defies the tenets of evolution. And yet they're suddenly just all there. We'll just ignore that. Well, anything that doesn't fit, we just... I'm reading a fascinating book. There's a guy, two guys, can I even remember their names? One is Amos Dvorsky. I'm probably butchering his name. And the other guy is Danny something. This is worth looking at. This is way more valuable even than our molarity and molality. Didn't even know you're getting this is bonus stuff today. Okay, let's see. Dvorsky. Kahneman, that's his name. I'm killing his name, Kahneman. They won the Nobel Prize for their work on just this stuff. Okay, let's see here. Are you serious? They don't have their names. Is it Danny Kahneman? I gotta have their names. What's the name of the book I'm reading? It's called The Undoing Project. Come on, give me their names. Okay, Daniel, here it is. Daniel Kahneman, and the other one is, oh, it's Tversky, Amos Tversky. I'm listening to it, so it sounds like Dversky. So these two guys, psychologists in like the 40s, 50s, 60s, 70s, who began to study our process of thinking and knowing. And in particular, at least the part that I'm looking at right now, is they're looking at our ability to predict things and to make conclusions. And so they find several things. One is the idea of like a recency bias. They call it availability. Oh, what are some of the other issues that they run into? One that they were just, like literally as I was driving here, they were talking about that. We call it the hindsight bias. So the idea, one of the ideas of like availability is that we will make our theory of whatever out of what we think we see, out of whatever is available. Mm-hmm. And so we'll just grab at it. And whether it's valid or not. And by the way, these things are happening subconsciously. We're not even aware of them. Mm-hmm. And so we will put pieces together that should not go together, but in our minds they'll be concrete and we'll stand on it. So like they're looking at that with history, with this hindsight stuff. So things that no one could predict. They did a study. So they, what's his name? The crook guy, Richard Nixon, was going to China. And so they had students make predictions about the likelihood of certain events happening. How likely is it that he meets with, the president of China like at least one time? How likely is it that it sparks an uprising? How likely is it that Jewish communists meet with him and get arrested? Just all these potential, like just any potential outcome, tons of them. Give it a probability. Then they come back afterwards. And so everybody filled these out. And they come back afterwards and they go, what probability did you assign to each thing? And they don't remember exactly. But essentially all you have to do is go, what would I predict happened? Well, they now predict that that the event that did happen, they greatly exaggerate. Like say that he met with Chairman Mao or whoever, I don't remember who the chairman was at the time. Say they gave it like a 5% chance of occurring. Okay? Well, now they think that they estimated that to be at like a 50% chance.
Because it happened.
Because it did happen. And so there's this hindsight that they're not even aware of. And they're talking about how this impacts the writing of history. People assume that what they saw, they knew, and they put these pieces together, and so it's just like, you can't trust yourself in these things because you don't think clearly. Why was I talking about that in relation to science and in relation to, we have these biases, and the other thing that they see over and over again is that once you have a theory, you will make all evidence fit your theory. What you don't do, where this is important, is you never dismiss your theory. So they did this. So they say somebody conducted an experiment, and they found according to all their data, there should have been 25% of A and 50% of B and 25% of C that occurred. Okay? And they ran this data, they ran this experiment, and what they actually got was 10% of A and 10% of B and 80% of C. Okay? And they asked them these questions. How would you advise these experimenters? Should they, change their theory? Should they, B, run the experiment several more times? Or should they seek to understand the phenomenon that they observed? Well, Tversky and Kahneman say, actually, the thing, and they were doing this with known stuff. Maybe there were poker chips in a bag, 100 of them, and so they know there's 25 of A, there's 50 of B, there's 25 of C. It's a known, but you only drew 10. They had each person draw 10, and then they drew 10, 1, 1, and 8. Okay, so it's a known versus randomness. Well, good science says run the experiment several times.
I would say C.
Can we trust this? But they always went somewhere like this. They would not scrap they wouldn't scrap their mindset. They didn't see a problem with their mindset. They didn't see a problem with their theory. They saw a problem with phenomenon.
Like what happened. So
Yeah.
let's see what happened to see if.
So you have an innate desire or tendency to defend what you believe in, whether it's right or wrong. Even in opposition, even in evidence to the contrary, you will defend your paradigm. And so instead of, really, you ought to just pull back and go, well, let's do this again, let's see. They talk about this in a number of different ways. They said throughout the bombings of London in World War II, all of England was convinced that they were targeted. Like specific locations were targeted because certain spots were hit over and over and over again. So they must have, those must be the direct hits and these must have missed because of randomness, right? Because it didn't feel random, it felt like there was a pattern. That's another thing, is we tend to see patterns where there aren't patterns that they found over and over again. If they gave you, you don't need everything that I've been listening to in this book, and I don't know it well as I need to. But then they had people who study randomness go back and look at these and plot them, and they found, no, this is exactly what you should expect. Because in randomness, there are clumps, there are clusters. For example, odds are a minimum of 50% that if I have 23 people in a classroom, 2 of them have the exact same birth date. Statistically,
it's hard to have.
We should have at least 366 people before I have a duplicate birth date, right? Because I know if I have a large enough sample size, that's the rate it would go. But that's not how small samples work. In small samples, inevitably you get clusters. So people who've done samples of samples have found that if I have 23 people in a room, I have better than 50% odds that 2 of them have the exact same birthday. They ran studies on students, like questionnaire type things. You got hospital A and hospital B. Okay. And this one's huge. This is a big hospital. This one's a small hospital. Okay. They said they observed births in this hospital for a month. Okay? And in one of them, 65% of the births were boys. Which hospital was more likely to have produced this?
I'd say the big one.
And so did almost all the students. But it's wrong. Because this is a very small sample. We know that given a big enough sample, it's going to come out to be 50-50. But in a small sample, randomness has a far greater impact. 15% is significant, right? I have to get into all that, but in significance and those things. But I am more likely to be off by 15% in a small sample. If the sample's small enough, that might be 1 kid. 1 extra boy born compared to a girl. Whereas in a big hospital, that might be 15 extra boys, But so we just don't account for randomness. We'll assign order where there is none. We have a theory and we're reluctant to get rid of it. We think we know things that we don't know, and we don't even know that we don't, we're so completely oblivious.
We don't know except that we don't know.
And we don't question ourselves. So you get a theory like evolution, you see it everywhere. And wherever you see it and it affirms it, it just affirms it. And the things that don't affirm it, you look for, well, what's wrong with that? Not what's wrong with my theory, or, let's take a step back and look at the whole thing. Kuhn. This is a name to know. So he wrote a book called The Nature of Scientific Revolutions. And he coined a very important term. I thought we were going to be doing chemistry today, but this is good stuff. Thomas Kuhn wrote one of my favorite books of scientific philosophy, I guess is what you have to call it. And I don't know the timing of his writing compared to Tversky and these guys. There's a lot of similarity in their thinking, though. So this is worth maybe someday catching. Thomas Kuhn, and it's The Nature of Scientific Revolutions. And he invents a word that was not there before, and it's paradigm. Everybody's heard of it, but you didn't know that this word didn't exist before like 1950. He made this up, he coined this term. And he describes a paradigm essentially as the lens through which we filter and see everything. So it's made up of all of our assumptions, all of our biases, all of our everything we think we've learned. It comes together, it forms a paradigm, it's our worldview. It's how we process everything. And you know what makes it into our paradigm? What makes it in is things that fit our paradigm. Well, that makes sense. But we're reluctant to receive, much less perceive, things that don't fit our, like, sometimes you consciously just reject something, other times you just miss it. You don't even see it. Because it doesn't fit. So one of the things he says about paradigms is they are resistant to change. They don't change. They have to be smashed. Like they literally have to be destroyed.
Like literally have to, something really shocking.
Like, is Earth flat or is Earth round? Like that. There's so much evidence that the Earth is round, but nobody believed it was round. Believed it was flat, right?
Mm-hmm.
It required a smack. Like that's why they call it the Copernican revolution, right? That things like the Earth is not the center of the universe and it's not flat. It's a revolution.
Changed everything.
Look here, the nature scientific revolutions, because there are just these moments in science where things don't just slowly shift. It's not this slow progress from the dark ages to the modern ages. It comes in smashes and everything gets destroyed and gets rebuilt like that. And it happens, we see these from time to time, especially in different fields. Well, this idea fits with Condiment and Tversky. We don't even know. We actually subconsciously defend. We don't even mean to.
It just happens.
And so, you asked me about, science and religion, and like I look there and I go, you just won't even look at these pieces that don't fit. You won't look at the gaps. You want to ignore them. And this is, scientifically, this is the most important gap. That you have to overcome this. There's no explaining it, unless there is a maker. All right, well, we'll pick up next time. I hope that will be profitable in life. We should have that lecture today instead of at the chapel.
At the chapel. I mean, that would be cool.
Still might have the same results. Still might would have most students go, oh my goodness.
But I mean, that would be cool. That would.
I'd have to know a little better what I was talking about. See you, man.